So the objective of this lesson is to understand and apply the concept of substitutions when integrating. So when we're doing integration by substitution, we're essentially drawing on the principles of the chain rule. So the chain rule can be written in two different ways. One way is d dx of some composite function, f of g of x, is the derivative of the whole thing times by the derivative of the inside. And you may be familiar with that. And then another way of writing it is dy dx equals dy du times du dx. Okay, and we use the chain rule. We use the chain rule, but in reverse when we're doing integration by substitution. So I know that if I integrate dy dx with respect to x, I'll get y. But then it also means I can integrate y with respect to u times du over dx, and that should also give me y, right? So I can integrate something with respect to another variable which I define, which is u, and then for the top equation, if I get an integral in the form of f dash g of x times g dash x, I know that's going to be f of g of x, just working from the chain rule backwards. And if you don't understand that now, it's okay, I'll go through some examples. So in this first example, I'm asked to integrate the following: 3x minus 1 squared. So if we were taking the derivative of 3x minus 1 squared, well, we'd recognize its chain rule, and the first thing we'd do is we'd let u equal 3x minus 1. And I can do that with integration the same way. So I can let u equals 3x minus 1, and now I have an integral of 3u squared dx, right? But I can't just integrate this just like that. Oh, sorry, this is not 3x squared. Sorry, this is just u squared. I can't integrate it just like that because my variable inside is u, but on the end I have dx. They're not the same variable, so I can't integrate like that. So I need to write dx in terms of du, so that u squared, and I have a u squared and a du together. So I can use this equation that I've made, u equals 3x minus 1, and now I have du dx equals 3. And with du dx equals 3, I can actually treat du dx as a fraction and write dx equals du on 3. So now I can rewrite this integral as u squared, and instead of dx, I'll write du on 3, which is the same as if I wrote 1/3 u squared du. So now I can integrate this as normal. I raise the power, and then I divide by the power when I'm integrating power functions. So this will become 1/3 u to the power of 3, and now I'm dividing by 3, plus c, because this is an indefinite integral, so I always need plus c, and I will get u cubed on 9 plus c, but I should write this in terms of x. U is 3x minus 1, so 3x minus 1 cubed on 9 plus c. It's that simple. Onto another example. Again, I do the same thing. So I have sine of 2x plus 1. I can say the inside is 2x plus 1. So I'll have let u equal 2x plus 1. Now I have du dx equals 2. And I can say dx equals du on 2. So now my integral becomes sine of u, and then instead of dx, I'll have du on 2, which is half integral sine u du. When we integrate sine, we should get negative cos. So this will become negative half cos u plus c. And then I'll write this in terms of x, So this will be negative half cos 2x plus 1 plus c. Okay, so this is a bit different to the previous questions. It's a special case for integration where we have a variable x under a radical, so it makes it a bit more difficult to integrate it. So usually when we have x under a radical, we can let whatever is under the radical, or whatever's under the square root, or whatever, we can let it equal u. So if I let 3 minus x equal u, I will have integral of x root u dx, and then I want to write all the other x terms that are outside of the radical. I want to write them in terms of u. So if 3 minus x equals u, then I'll have 3 minus u equals x. Right, so x equals 3 minus u, so I can write this as 3 minus u times root u, and this is still in terms of x, so then I should find du dx, and I have du dx from here. Du dx equals negative 1, so this will be 3 minus u times root u du on negative 1. I can bring the negative 1 outside because it is a constant. So now I have this, and I can expand this, so I'll have 3 root u minus, this is u and this is root u, so I'll write this as u to the power of 3 on 2, and root u I can just write actually as u to the power of half. And now if I just treat this as a normal function to integrate, then I'll raise the power, so half goes to 3 on 2, half will go to 3 on 2, and then I'm dividing by 3 on 2, which is the same as multiplying by 2 on 3. So 2 on 3 times 3 is 2. And then for this one, I'm raising by 1, so 3 on 2 becomes 5 on 2. Dividing by 5 on 2 is the same as multiplying by 2 on 5. So I'll have this. So this will be my expression, and I'll have a plus c on the end. I can multiply it out. Plus 2 on 5 plus c, like that. And then I can write this in terms of x. So this will be minus 2, 3 minus x to the 3 on 2 plus 2 on 5, 3 minus x to the 5 on 2 plus c, and that'll be my final answer. Okay, and this is just another example to reinforce that point. So I have x squared out here, and then I have x plus 2 under a square root. Just keep in mind that for these kinds of questions, the x, the linear term like x plus 2, or it could be anything, doesn't necessarily have to be under a root. This could be x plus 2 to the power of 3 on 2, anything like that. So it doesn't just have to be a square root, but in these examples, I'm just using square roots. So I'll do the same thing as before. I'll let whatever's under my radical equal u. So I'll let x plus 2 equal u. Then I'll have x equals u minus 2, x squared equals u minus 2 squared. So I'm just getting x squared in terms of u. And then I'm also going to find du dx equals 1. So that's all good. Then I'll have dx equals du, right? So then if I just write this integral in terms of all u, x squared becomes u minus 2 squared. This root x plus 2 becomes root u, and then my dx becomes du, du on 1. So that's just du. And then I will evaluate this as normal. So if I expand this, I'll have u squared minus 4u plus 4, all times square root u du. So now I have u to the 5 on 2 minus for, this should say u, it looks more like an a, 4u to the 3 on 2 plus 4u to the half, and then if I raise 5 on 2, I get 7 on 2. Then I need to divide by 7 on 2, which is the same as multiplying by 2 on 7. Same here, this becomes 5 on 2. So then dividing by 5 on 2 is multiplying by 2 on 5. So 2 on 5 times 4 is 8 on 5. And then this goes to 3 on 2. And then I divide by 3 on 2, the same as multiplying by 2 on 3. So that is 8 on 3. And then plus c. So then overall I'll have 2 on 7. X plus 2 is u, so x plus 2 to the 7 on 2 minus 8 on 5, x plus 2 to the 5 on 2, plus 8 on 3, x plus 2 to the 3 on 2, plus c. So yeah, I get a pretty long equation, but this will be my final answer, like this. Okay, so we're going to move on from the previous substitutions, and they were all linear substitutions. So I always substituted I always substituted like x plus 2 or 3 minus x, all linear equations for u. So now in this case I'm subbing in non-linear things. So before, when I was talking about chain rule, I said ddx of f of g of x equals f dash g of x times g dash x. So then if I took the opposite of that, basically if I have an integral f dash g of x times g dash x dx, that's going to be f of g of x plus c, which basically just says, well, in this example I have cos of x squared, and I noticed that the derivative of x squared is actually 2x. So I actually have an equation in this form, but I'll show you how to do this. So if I let the inside function x squared equal u, then I'll have du dx equals 2x. So that gives me dx equals du on 2x. So if I write this expression in terms of u, I'll actually have 2x cos u times, and then du on 2x. And you see here that this 2x and this 2x will actually cancel each other out. So this should give me integral of cos u du. And when I integrate cos, I just get sine. So this will become sine u plus c, and then I'll put it in terms of x. So this will become sine x squared plus c. And that'll be my final answer. Yeah, so this is another example of that non-linear substitution. So if I look at this expression, I notice that the top of my function is x and the bottom is 2 minus x squared, and if I took the derivative of the bottom, it would give me negative 2x, and that would allow me to cancel my x's on top with that negative 2x. That probably doesn't make a lot of sense, so I'll just show you in the example what I mean. So if I let the bottom equal 2 minus x squared, then I'll have du dx equals minus 2x, dx equals du on minus 2x. So if I write this all in terms of u, I have to be very careful because the terminals also need to be written in terms of u. So if u equals 2 minus x squared, then the terminals for u will also be the same thing, right? So if u equals 2 minus x squared, this is 0, then the terminal will be 2 minus 0 squared, which is 2. For this one, -1, the terminal will be 2 minus -1 squared, which will be 1, right? And then I'll write this, like, I'll keep the x on top. This is u, and then du on -2x. And notice when I write it like this -2x I'm dividing by here, and this x up here cancel each other out. So when you're given an integral, you're basically looking for opportunities to cancel out your variable, x in this case. So when I've written it like this, now I can say, okay, that's 2 to 1 of 1 on u du, and since the x cancels out, this is just du on -2, so -2 is a constant, so I can take it outside of the integral. -12 2 to 1 1 on u du. And now I have my expression just in terms of u. My terminals are also in terms of u, so everything's good. I can integrate this as normal. So this is going to be the integral of 1 on u is log EU. This is log EU, and my terminals are 2 and 1. So this is -12 log E2 minus log E1. Log E1 is just 0. So this is just -12 log E2. And that's my final answer. It's a definite integral, so I don't need plus c. Okay, and just as a final example, again, it's a non-linear substitution. I'm looking for opportunities to cancel out parts of my integral by finding an expression for u that when I differentiate it, I can cancel stuff out. So if I look at this, well, if I took the derivative of cos 2x, I would get minus 2 sine 2x, and that would actually cancel out nicely with this. So I'll let u equal cos 2x. du dx will be minus 2 sine 2x. So I'll have dx equals du on minus 2 sine 2x. So I can write this as 2 sine 2x times square root of u on du on minus 2 sine 2x. So that 2 sine 2x will cancel with this one. I'll just get a negative sign, so I'll stick that out front. Negative integral square root u du. And square root u is really easy for me to integrate since that's just u to the power of half. So this will just become negative u to the half. And then I'll raise the power, so u to the 3 on 2. And then you divide by the power. So dividing by 3 on 2 is 2 on 3. And then I'll have plus c. And then I'll write that in terms of u. So u is cos 2x. So I have minus 2 on 3. Cos 2x to the power of 3 on 2 plus c. Okay, and that will be my final answer. You might be wondering, well, okay, but I could just as easily take the derivative of sine 2x, which will give me 2 cos 2x. So why can't I cancel like that? Well, I have cos 2x under a radical. It's square rooted. So if I took the u equals sine 2x, I would get du on cos 2x. And that wouldn't cancel nicely with the square root cos 2x. So I've just chosen cos 2x to equal u because when I take the derivative, I'll have du on 2 sine 2x, and that'll cancel nicely with this. Okay, there's no formulaic way of trying to figure out how to do an integral using substitution. It usually just takes a lot of practice and recognizing certain types of integrals before you get into the hang of it. Okay, so that's the end of linear substitutions. I hope it was helpful for you.